Modern data centers face a bottleneck that has outpaced physical fiber capacity. As networks expand, the primary constraint on throughput is the speed of the routing decisions required to move every packet. The backbone of the global internet still relies on iterative search algorithms like OSPF and Dijkstra. To move data, routers must calculate the best path through a sequence of step-by-step guesses. This search process is a combinatorial problem. Path computation time scales exponentially with the network nodes, reaching an O(e) log v complexity that makes every expansion of the network more computationally expensive. This scaling model cannot survive the sub-millisecond latency requirements of 6G URLLC. In these new environments, there is simply no time left in the budget for an iterative path search. Iterative search algorithms are reaching their physical limit today. Hyperscale traffic requires a method that eliminates the search entirely. The Spectral Geodesic Protocol, or SGP, replaces iterative logic with a method derived from circuit physics. Instead of finding a path, it treats the network as a single conductive field. This version 19.0 benchmark demonstrates a 1350x increase in packet forwarding speed compared to legacy OSPF. The speed gain is matched by a 240x improvement in recovery. When a link fails, SGP reconverges in 0.12 milliseconds, nearly 250 times faster than legacy systems. SGP achieves this by transforming routing from a combinatorial search into an O(1) linear algebra operation. By modeling networks as potential fields, SGP shifts the routing workload from slow software search loops into a pre-calculated mathematical flow. The model begins by converting standard network ping, or latency, into a measurement of electrical conductivity. High-latency links are treated as high-resistance paths. These localized values are mapped into a spectral matrix. This chart visualizes the network as a resistive circuit, where green lines represent high-conductance, low-latency fiber. The protocol uses this data to calculate the Laplacian Pseudoinverse. This core equation generates a continuous mathematical potential gradient across the entire topology. We see the geometry of flow when a packet is injected at a source node, visualized here as a high potential peak. This fixed potential difference makes the destination the lowest point, creating a slope that directs traffic towards its target. In this model, data packets follow the pre-computed mathematical gradient, similar to the way electrons follow the path of least resistance through a physical circuit. The primary challenge for spectral routing has always been the computational cost of updating the matrix. If a single fiber link is severed, the entire model must be recalculated. Performing a full matrix inversion is an O of n cubed operation. For large networks, the math required to handle a single link failure becomes too heavy to execute in real time. SGP bypasses this barrier by using the Sherman-Morrison rank 1 update to adjust the matrix. Instead of a global recalculation, Sherman-Morrison treats a link failure as a localized perturbation. The protocol updates the affected coordinates without disrupting the rest of the matrix. This reduces the complexity from an O(n) cubed operation to an O(n) squared operation, enabling updates in microseconds. This efficiency allows the network to self-heal autonomously upon failure, maintaining connectivity without waiting for a centralized controller to recalculate every path. Even with O(1) mathematical complexity, the protocol would still fail if it was bottlenecked by the physical speed of the router's memory. Fetching data from standard RAM takes over 200 clock cycles. Accessing the CPU's L1 cache takes only 4. SGP eliminates this wait time by shrinking the routing table until it fits entirely inside the cache. This requires extreme compression of the forwarding information base, or FIB. By encoding decisions as compact integer arrays, the protocol compresses the FIB down to just 224 bytes. This allows the entire routing table to reside permanently inside a single L1 cache line. An L1 resident FIB transforms routing from a memory access task into a pure, uninterrupted execution of the processor's clock cycles. The final hardware bottleneck is the floating point unit. Standard decimal math can cause pipeline stalls that slow down the processor. SGP avoids these stalls by using zero-float arithmetic. The system bypasses the floating point unit entirely, performing all routing calculations within the processor's integer ALU. The protocol uses bitwise vectorization to encode all valid routing options into n-bit registers. This allows the processor to evaluate multiple paths simultaneously. The exact next hop is then selected using the CTZLL instruction, a hardware-level command that counts trailing zeros in a bit mask. This combination of integer logic and hardware instructions allows the processor to determine the optimal route in a single clock cycle. By operating purely on bare metal integer instructions, the system can sustain the extreme speeds required for hyperscale traffic. Traditional routing logic is fragile. It relies on a single, fixed path to move data, leaving it vulnerable to congestion and failure. SGP is more robust. By creating a broad potential field, it allows traffic to disperse across the entire topology, naturally balancing the load. The v19.0 engine achieves 953 million packets per second on commodity 8-core hardware, a throughput increase of nearly 1 million times over legacy OSPF. This performance was sustained with exactly 0% packet loss across a 100 million packet test. SGP succeeds by combining the topological intelligence of a Laplacian matrix with the raw execution speed of an L1 resident integer engine. SGP is ready for immediate use in any closed-loop network. It does not require a global overhaul to deliver its full performance. In AI training clusters, the potential field provides native load balancing for massive data flows without the collisions common in standard hashing methods. In 5G and 6G backhauls, it provides the microsecond reconvergence required to meet the world's strictest latency standards. The era of iterative, search-based routing is reaching its physical limits. The future of high-throughput infrastructure now depends on the geometry of flow.